Hello everyone and welcome back. I'm Mahnur and today we'll be continuing on with the chapter of kinematics once again. Last time we had not only discussed the ABCs of kinematics by learning some fundamental terms, but we had also learned how to conduct a qualitative analysis of moving objects through the graphs of kinematics. So now that we've gotten the qualitative side of things out of the way, now we can tackle the second aspect of kinematics. For this, we'll be dealing with what we call the equations of motion. These are basically a set of equations that link the following 5 terms that you can describe for any kind of object that's moving: a final velocity v, an initial velocity u, constant acceleration a, displacement s, and then finally a time interval t. So in that case then, the following equations are basically equations of motion that apply to any object that's moving with constant acceleration. And they are as follows: v equals u plus at, s equals half times u plus v times t, s equals ut plus half at squared, and then finally 2as equals v squared minus u squared. But before we can even try to use these equations one by one, we should first understand where they come from. In other words, we should know how these equations are derived in the first place. And so, we will tackle each of these one by one and figure out how are they derived. Starting off with the first and perhaps the most straightforward equation, that is, v equals u plus at. This equation is so straightforward to derive, in fact, that we can start off with an equation that we're already familiar with, starting off with acceleration as the rate of change of velocity. And here we have described it as a equals v minus u over t. Now the goal here is to make v the subject of the formula. And to do that, we have to conduct the following 2 steps. We will first multiply t on both sides to get the following expression and then add u on both sides. And so we arrive at the first equation of motion, v equals u plus at. Now we can move on to the second equation of motion, s equals half times u plus v times t. To derive this, we can actually make use of a velocity versus time graph, specifically one that we can draw for an object moving with constant acceleration. We know that this graph works because a straight line like this has constant gradient. And since we know that for a velocity versus time graph, the gradient equals acceleration, therefore we know for a fact that this shape works for any object moving with constant acceleration. Now let us mark off an initial velocity u like so, and then a final velocity v, and both u and v have some time interval between them labeled t. Now if I shade this region as follows, I've basically constructed a shaded region that I wish to find the area of, and that will basically be equal to displacement. Now if I recognize the shape of this shaded region, I'll immediately recall that it's the area of a trapezium, in which case displacement can be found by simply evaluating the area of this shape. We already know what the formula is. It's half times sum of parallel sides times height. In accordance with our diagram that we've drawn on the left-hand side, these parallel sides are basically u and v, in which case the sum of parallel sides basically becomes u plus v, whereas the height of this trapezium is t, in which case the expression for displacement becomes half times u plus v times t. And so we have arrived at our second equation of motion. Now let's move on to the third equation of motion, that is s equals ut plus half at squared. Now this equation can actually be derived from the previous 2 equations we just found out, that I've labeled here as equation 1 and equation 2. The step here is simple. All we need to do is plug in the first equation into the second equation. What that involves is a replacement of v in the second equation with u plus at, and we get the following equation. All we need to do next is to simply expand the bracketed terms, and we arrive at ut plus half at squared, which is primarily the third equation of motion. Now that's great. Now we're ready to finally deal with the last equation of motion, that is 2as equals v square minus u squared. Once again, we'll be using the first 2 equations that we just found out, The only difference here is that the first equation will be slightly rearranged, such that we'll be making t the subject of the form. And that gives us b minus u over a that I've labeled here on the left-hand side. And then the second equation stays as it is. The next step is to replace the t in the second equation with the t that we have in the first equation. This kind of a direct plugging in will give us the following expression. Now, if we stare at the numerator pretty carefully, we recognize that this is an mathematical identity that we're already familiar with, which is the following, that a plus b times a minus b equals a square minus b square. So we can easily make the numerator far more simple than this and rewrite the expression as s equals u square minus b square over 2a. Now it's just a matter of rearranging it and simplifying the expression to get 2as equals v square minus u squared. And so we arrive at our fourth and final equation of motion. So we have reached our third checkpoint. This time, what we've done is understood the four equations of motion that link v, u, a, s, and t with each other as long as the object moves with constant acceleration. Done watching the video? That is great. Find the notes and topical questions related to this video and many more free resources related to your A-level subjects on our website. You can find the link in the description.